to another It's Not Quantum Physics. Today we're going to talk about applications of SHM, and we're going to link our understanding of SHM to both springs and pendulum systems. Applications of SHM, that's what we're going to cover today. And make sure you've had a look at the specification to know how this all fits in. So we're going to start with looking at a spring. So I'm going to look at a spring in three different positions. Now, we'll look at a spring that's been compressed. If this is its natural length, as it would normally be. Imagine it has a mass on the end. In fact, let's put a little mass on the end there. We'll look at a spring that is at the natural length. Same spring, it's just moved a bit further through the cycle. And we'll look at a spring that has been stretched beyond where it would naturally sit. So three different situations. If we were to look at this on a graph, what are the three different points we're looking at? Well, we're looking at the fact it's been compressed, so I'm going to call that, let's call that negative. So we'd have started down here, come through to 0, and let's say these are our amplitudes, our maximum displacements. Then we can say A is going to be this first point, B is going to be the point where it goes through 0, and C will be the maximum amplitude in the extension. Right, so why am I talking about a spring? Well, I'm talking about a spring because we have to talk about the forces. In fact, let's just be a bit more definite with what we're talking about here. So we have our maximum amplitude. Very good drawing, but never mind. And we have our minimum amplitude. Okay, so this is what we're looking at. Now, if I was to draw forces on here, we really only have, well, we have the force of the weight that's pulling it downwards, but that stays the same. So I'm going to ignore that for the moment. I really don't care about the force of the spring itself. Now, initially, when I've compressed my spring doesn't want to remain compressed. It's going to want to stretch outwards. It's going to want to get back to its natural length. So there is a restoring force acting that direction to push the spring back to that 0 length. Well, when I'm at the 0 length, the spring is at the correct position. So in fact, there's no force at this point because we also know there's no acceleration. So there's no force, there's no acceleration. But when I stretch my spring, when it's reaching point C here, there's going to be a restoring force acting in the opposite direction. So we've got these forces that are acting upon the spring, which is trying to return it to where it should be. The restoring force is what we call them. So the force on the spring acts towards the equilibrium line, or the mass equilibrium line if you want to be more specific, but we'll call it the equilibrium line, trying to return the spring to the original length. And we call this the restoring force because it's trying to restore that spring back to the position that it should be. It's trying to restore that spring. Now, we already knew this. This shouldn't be anything new because in the last couple of videos, we've talked about the fact that acceleration is proportional to the negative displacement. And if we know Newton's second law, which hopefully we do, F equals ma, then we can also say that the force must be proportional to the negative displacement. So hence, if I'm moving my spring in a positive direction, my force must act in a negative direction against it. And if I'm moving my spring in a negative direction, my force must act in a positive direction, always trying to return to this equilibrium line. And it's this thing called the restoring force is what we're talking about. So what makes something be in simple harmonic motion? What's sort of the definition? What you're expected to know? Well, you're expected to know two things. You're expected to be able to say if the acceleration is proportional to the negative displacement, then it's in simple harmonic motion. And also, if the force is proportional to the negative displacement, it's in simple harmonic motion. And that is what's going to cause, so both of these two things, and they're interlinked, and we kind of know that, don't we? So let's put some chains in between them. They're interlinked because obviously of Newton's second law, because that's what we're bringing here to help us with our understanding. So if that's true, then the object is going to oscillate with SHM. So if these are both true, the object will oscillate in simple harmonic motion. So that's our definition of simple harmonic motion. If the acceleration is proportional to the negative displacement, so the acceleration always acts in the opposite direction of the displacement, and if the force always acts in the opposite direction to the displacement, then the object will oscillate in simple harmonic motion. Okay, so that's kind of the definition of SHM. We've kind of got there. 4 lessons later, 4 videos later, we're explaining what SHM really is. So let's look at a simulator to actually understand whether this is true and how true it is. So we'll take a mass, and we'll attach it to the spring. So the spring is oscillating backwards and forwards. Let's have a look at those velocities and let's slow it down, because we've talked about this and we should now be able to understand it. And let's put the equilibrium line in as well. So when the mass reaches the amplitude, you can see the velocity is changing direction. And it reaches 0 before it changes direction, and obviously is at its maximum value as it passes through that equilibrium line. So we can see that that velocity is acting in the same direction. Well, let's now switch to the acceleration. As the mass moves further away from the equilibrium line, you can see that that acceleration is trying to pull it back to the centre. And this is all due to the idea of the restoring force. So here we've got our net force. In fact, let me just switch that to the spring force first. So here we've got the spring force. It's always trying to return the spring back to where it wants to be, and we haven't got any compression here really. It's just that the force is getting a bit smaller. But if we look at the net force, this is going to link with what we've been saying, that the actual net force is always acting towards that equilibrium line, and the size of the force gets bigger the further away you go. So the force is proportional to the negative displacement in the same way that the acceleration is proportional to the negative displacement. So this object is in simple harmonic motion because of the fact that the acceleration is proportional to the negative displacement. The force just comes with it. Okay, so here we've talked about springs. Let's just go back to the visualizer because we're going to go for the next part, and we're going to describe springs, because springs are a very simple system for simple harmonic motion. So springs, how can we change the frequency? Okay, so if we want to change the frequency, we know that that's also changing the time period, because those two are linked. Remember that frequency is equal to 1 over the time period. So if I want to change the frequency, there's two things I can do. The first thing I can do is add extra mass. So what I'm saying is I've now got a spring. Here's my spring. But instead of a really small mass, I've got a spring, same spring, but I've got a giant mass. So we've added that extra mass to it. Well, if it has more mass, then it has a greater inertia. And the greater the inertia, the more it kind of wants to move and the harder it is to stop it moving. So if it's got a greater inertia, it's going to be slower to turn around. Okay, it's going to be harder to turn it around. It means it's going to be slower to turn it around. So it's going to have the displacement is going to take longer. So the displacement is longer, and if the displacement is longer, the time period will increase. And if the time period increases, then the frequency will decrease. So if we add a greater mass to our spring, we should see that the time period has increased. Well, let's find out. Let's check that. We'll go back to the simulator and we'll add a greater mass to it. So our simulator was still swinging with our 100 grams, and in fact, let's time it. So we'll go from peak amplitude through the equilibrium point to lowest amplitude back to peak amplitude. So 0.084 seconds. Remember, we're on slow here. So now let's swap that one off and let's put a 250 gram mass on. Okay, we'll wait for it to go back to peak amplitude and we'll time it. Obviously, if you're doing this in a lab, you would time it for 10 or 20 oscillations and divide it by 20. But because we are doing this with a simulator, we can slow it down. We can see. There we go. So 1.28. So we can see that that time period has increased because, look, you need a greater force. You need greater acceleration to pull it back so it can actually move through a greater displacement. So the amplitudes are greater. So therefore the whole displacement is greater. So it is going to take longer for it to move. Okay, so that's our first one. Let's talk about the second one. What else can change it? Well, the weaker the spring is. And we define the spring by the spring constant, K. Now, a weak spring might look like that, and a strong spring might look like that, because it needs more force to pull this by a meter than it does to pull this by a meter. Remember that that's what we're talking about when we talk about the spring constant. So a weaker spring has a lower restoring force. In other words, it can't pull back as much as a stronger spring. If it's got a weaker or lower restoring force, you know what force can link to. It can link to acceleration. So it must have a smaller acceleration. So it takes longer for it to decelerate at either end. And if it takes longer to decelerate, then the time period must increase. So the time period will increase, and as we know, that's linked, so the frequency will decrease. And this is a low spring constant, and this is a high spring constant. Well, let's go back to the simulator and let's see if we can simulate this. So we were oscillating still with our 250 gram mass. We're going to make sure our mass is the same. We're going to have one very, very light spring constant, and let's really go for the heavy one at the other end. We'll add 100 to that one. Let's just pause it for a second. We'll go right to the top, and we'll add 100 to that one, and we'll push that one right to the top as well. So we should see that spring 1, in fact, let's try and make this fair, roughly starting from the same point. Spring 1 should take longer to oscillate than spring 2. And we see that because, remember, spring 2 now has got a much greater acceleration. And if we're looking at a net force, it's much greater, so it can turn around much quicker when it reaches those amplitudes, those maximum displacement points. And that means that it also kind of has a bit more, well, it has a higher velocity as it's moving through the centre. So we can see that a high spring constant is going to increase the time period and so decrease the frequency. We could prove it by doing the timings, but I don't think we need to. I think we can see it by what we can see on the screen. Okay, so let's be a bit more definitive with what we're talking about here. Because we can say that the time period for the spring to oscillate is going to be proportional to the extension of the spring. The greater the extension, the greater the time period for it to oscillate. And we know that if we want to take away that proportionality, we've got to multiply it by a constant of proportionality, which we'll call k. And k in this case is going to be our spring constant. In fact, I take it back, that's not the time period, that is the tension. Sorry, the tension of the spring is proportional to the change in length, the extension. So the tension then is equal to K times X, which we know, we've seen that. F equals Kx, we saw at GCSE. It's nothing new from there. Okay, so at a displacement, which we'll call X, the spring force, the tension of the spring, is the restoring force. So we can say that the change of that force of the spring, tension of the spring, is going to be minus Kx. So we can define acceleration. So acceleration is equal to, this is what we're, in fact that's not, but equals, acceleration is F equals ma, which we know, Newton's second law. So we can say minus k lots of x is equal to m times a. So therefore, a is going to be minus kx over m. But we also know that acceleration is equal to minus omega squared multiplied by x. So minus omega squared x is equal to minus kx over m. Alright, solve this for omega squared. Okay, we can cancel the x's, we can cancel the minuses, so we can say that omega squared is equal to k over m. So we have defined our angular velocity in terms of our spring constant and our mass. So this proves that the spring is in simple harmonic motion because it still stands to follow that acceleration equation we have for simple harmonic motion, which is the minus omega squared x. So object is in simple harmonic motion, and this is our last little bit here. So any object moves with simple harmonic motion if acceleration is equal to minus omega squared x. Important equation, important proof of how to bring together this idea of springs and simple harmonic motion. Okay, so proving that pendulums can also remain in simple harmonic motion, and we're going to start with a diagram here to explain it. So if I have got a pendulum at some part in its swing, then we'll call the length of the pendulum wire L, and we'll call the angle theta. Oops. And the displacement at that point there we'll call S. And we'll define this side as positive and this side as negative. So that pendulum obviously will swing backwards over in this direction in a similar way. So if we now zoom in to the forces that are taking place on that pendulum, because this is ultimately what we want to do, then we know we have got a tension acting up the string. It's that tension that's causing a circular motion that's allowing the pendulum to rotate round. We have got acting straight down the weight of the pendulum bob, and we know this angle is theta. So that actually allows us to decompose the parts of the weight into perpendicular and parallel to the tension itself. Because if that angle is theta, then this angle must be theta. So this will be mg cosine theta, and this will be mg sine theta. So that's the forces acting on our pendulum bob. Okay, and that allows us to see quite straightforwardly that we've got tension acting in one direction and we've got mg cosine theta acting in the opposite direction. And we can see what's going on. Okay, so it's displaced, this bob has been displaced from equilibrium and then let go. And it's going to oscillate around that lowest point, and it's going to move a displacement S backwards and forwards. And we know that we've got these two components of the weight that are coming from this decomposition of the weight acting vertically and splitting it into perpendicular and parallel to the tension. Okay, well, the restoring force in this case is actually still going to be the tension. It's not, in fact, I'll lie. The restoring force in this case is going to be the opposite of our mg sine theta. Because the restoring force is wanting to pull it back to the centre, mg sine theta is pulling it back to the centre, so we can say that F is equal to minus mg sine theta. So we can define our acceleration because we know that F equals ma. So A equals F over m. So this is going to be A is equal to minus mg sine theta divided by m. So that leaves with minus g sine theta. So the mass doesn't matter. And then we're going to use something called the small angle approximation. And it's kind of a mathematical trick here. So small angle approximation says that theta has to be less than 10 degrees, roughly. It's got to be around that. And if that's true, then we can say that sine theta is going to be equal to S divided by L. Because if we've got a small angle, then this is almost equal to the exact straight direction. If we go too big, then obviously we've got a greater displacement. But if we're looking at the distance from that 0 point straight across, if the angle's small enough, then we lose that curve. Okay, so that's where we're coming from here. So that allows us to go and say that the acceleration is going to be equal to minus g s over L, and we can also say that that's minus omega squared s, where s is my displacement, just go back up to the top and get rid of our diagrams. So if we're saying that acceleration is equal to minus gs over L, which is equal to minus omega squared lots of s, we can then redefine omega squared. So therefore omega squared is going to be equal to, so s is a gone, the minuses are gone, it's going to be g over L. So this object oscillates with simple harmonic motion because its acceleration is still proportional to the displacement from the equilibrium and always acts towards the equilibrium. Okay. So object oscillates with SHM as acceleration is proportional to the displacement, and the minus here tells us that, but and acts towards the equilibrium. What do I mean when I say that? Well, I mean that if I'm over this side, I have got my mg sine theta acting in that direction. Not worrying about the other forces because they're perpendicular to it. And if I'm over this side, I've still got my mg sine theta. In this case, it's going to be, well, we'll call that one minus, we'll call that one plus. It depends on which way we've defined it. But in this case, it's going to be acting towards the center. So whatever we do, it's always wanting to act back towards the center and is proportional to the distance we move away. The greater we move away, the greater the acceleration. Okay, the amount it wants to pull back in, and you can check that by looking at the angle and looking at the size you would get. So there's our proof. We've always got to talk about that acceleration being proportional to the negative displacement, and that is what's true for SHM. Okay, so we're just going to define the time period now in terms of what we know for this, this system. We know that omega is 2 pi f. And we know that omega squared is equal to g over L. So what we can say is that omega squared here is then going to be 2 pi f all squared, which can be 4 pi squared f squared. So therefore we can say I've got 4 pi squared f squared is equal to g over L. So let's redefine this as f. So f squared is going to be equal to 4 pi squared, 1 over 4 pi squared g over L. So f then is going to be 1 over 2 pi root g over L. But we also know that time period is equal to 1 over frequency, because if frequency is 1 over time, time is 1 over frequency. So therefore we can say that time period is going to be equal to 2 pi root L over G. As long as, and here's your caveat, theta has to be less than 10 degrees. That has to be true or our small angle approximation falls apart, and we can't have this proof without this bit here. So those two are linking together. So we can increase our time period by increasing our length. We could increase our time period by changing our gravity, by decreasing our gravity. And we can't do anything else with the 2 pi because that's just a constant. So it's changing the length. The time period is related to the length of the string, of the bob. Okay, and I will leave you to work out the tension of the pendulum, but if you need some help, have a look at page 24 in the textbook.